In this video, we'll apply a GradCAM to a UNet model trained for multi-class image segmentation. Let's see how we can visualize what the model is focusing on class by class. So our first question is, what is GradCAM? In simple terms, we can say it is a technique which helps us to understand where the model is looking when predicting a particular class. It uses gradient flowing back from a specific layer to generate a heat map over the input image. And it can be applied to any layer. What we mostly apply it to the last layer or mid layer, so that we can see what these layers are focusing on. And here is an example where you can see the classification model is particularly focusing on the main object, that is the dog. Now we'll use this GradCAM technique and apply it on a multi-class segmentation model. So now let's move on to the code. So for this video, I'm going to use my previous code where I've trained a UNet architecture on the weed segmentation dataset. Let me show you the results first. Okay, so here you can see the image, the ground truth and the predicting mask. And here you can see the values are matching. So you can see multiple result and it has two classes. So two kinds of weed. So now we're going to use this model and we're going to calculate the GradCAM. So let me close this folder. Yeah. So now we'll move on to our file. And first of all, we are going to import all the libraries which we need for this task. So here we are, we have imported all of them. Now we're going to write one function to get the layer, specific layer from the model. So here's that function. So we called it getConv layer. It take the model and the name of that layer. So inside we have a loop. We loop over all the modules which are there in the model, and then we match its name. And when the name is a match, we give that layer. Otherwise we raise an error that this specific layer is not found in the model. So this thing is really easy. Now let's do one thing. Let's move on to the main part from where the execution start. And let me start copying it. Okay, so here we are. So here you can see we have seeded the environment, then we have given the height and width of the input image, and here we are with our data set, and here we have our RGB code in case we require them, and then we have number of classes. So we are using a custom UNet with 3 output classes: background, weed1 and weed2, and our data set contain RGB images and their corresponding segmentation mask. Now we are going to load our trained UNet checkpoint. So with this way we have our model assigned and we have loaded the weight. Okay, now we are going to load the weight. Sorry. Okay, so we have loaded the weight into the model now. So let me just print our model just to check if things are working or not. Okay, so things are working, and from here we specifically can know which layer we want to get our heat map from. So this naming would be really helpful. Okay, so now we need to load our data set. Let me close this and remove this line. So here we are using the test data set, and we are using 10 samples for now because there would be too much samples and it would take time. Next, we're going to create a folder to save our results. And here's the folder, that is GradCAM. That would be inside the results folder. So it would be a subfolder, GradCAM. And inside that folder, we're going to save heat map according to class for each class. So we have 3 classes. First is background, weed1, weed2. So for each class, we're going to save the heat map generated by the GradCAM technique. Now the main function. So this is the main function which we're going to build called apply GradCAM. So it's going to take the model, then the save path, then the images, mask, basically their list, then size of the image, then the color map and the name of the layer. So here you can see we have specified D4 conv 5. So if I open it, so you remember D4 conv 5. So this is the last decoder block, specifically the ReLU output, on which we're going to get the heat map. We can change this, but for now let's do this, or even we can change it. Okay, we can see the encoder and the mid block and the decoder, where they focus on. Initially I'm going to start with the last decoder block and absolute last layer, so that we can easily see. So now let's move on to this apply GradCAM function. So first of all, I'm going to define it. So in this function, for each test image and each class, we compute a GradCAM heat map, compare it with the binary ground truth of that class, so that we can easily see where the model is focusing and whether that spatial area, that specific region of interest, is important to us or not, by evaluating it with the ground truth, even also for the background. So now we're going to loop over that test image and test path. So let me paste the code. So here we have a loop, and within each loop we have our x path, that is path of the image, and y path, path of the mask. So first of all, we extract the name, because we need to save the GradCAM, so we need the name. Then we read the image and save, make a copy of it. Then we perform some pre-processing on it, because we need to normalize it and make it a channel first. Then we expand its dimension, so finally converting it into a 4D tensor with its dimension as 1, then forwarded by channel, then height, and then width. So this is how it works. Then we have the ground truth, and we have resized it accordingly. Now we need to make another loop, okay, because we want to compute grade map for each class. Okay, so now we have one more loop. So here class index 1, 2, and 3rd. First 0, 1, 2. Sorry. These are the classes. Now we need few more functions. Okay. So first would be compute segmentation GradCAM. Okay. So inside it, I'm going to specify that. So this is our function. It take your model, input tensor, class index, and the name of that specific layer. Okay. So now we're going to move on to this function, compute segmentation GradCAM. And this is really easy. Okay, so let me define that function first. Okay, so we all know what this function take. This autocomplete is totally shit, I'm telling you. So first of all, what we need to do, we need to find the layer inside the model where we want to hook for the GradCAM. So we need to get that layer. Okay, so we got that layer. Next, we'll initialize a list, empty list, to store the activation and gradients, because we need them. So here are the empty list. Next, we need to define the hook. Please don't follow this autocomplete, and please tell me where to stop it, because I hate it, because it does not allow you to learn. Now here we have hooks. Okay, so the forward hook saves the output feature map of the specific layer, and the backward hook captures the gradient of the layer's output during back propagation. So this is what they do. Next, we need to attach hook to the layer. So now hooks are registered to collect data during forward and back propagation. Next, we need to make the prediction and get the class specific score. So here what we do, we apply the model, we get the per pixel probabilities via softmax, then we average the score over all the pixels to get the target class. This is simply used to compute gradient for GradCAM. Next, we need to back propagate to compute gradients. So this is how we're going to do it. After that, we're gonna extract the saved activation and gradient. So here we have the gradient and the activation value. Now we need to get the GradCAM, because this is the main function. From here the GradCAM basically start. Till now we are calculating all the values, but now we're going to directly work on the GradCAM. So now we need the weight. So we compute the channel wise weight by meaning it, perform a mean operation over the dimension 1 and 2, that is height and width, if you remember, if I'm correct. Yeah, height and width. Next, we're gonna have an empty GradCAM map, which we're gonna define like this. Okay, and now we're gonna do a weight sum of activation using gradient derived weight. See, like this, using a loop over the weights. So here, so this is I is basically index value starting from 0. Then in weights we have W. So what we do with GradCAM, we say plus equals to, we multiply the weight with the activation value. So this result in a 2D attention map, simple single channel attention map we get. Now what we need to do, we need to apply ReLU operation and normalize it and remove the hooks at the last. So you can see we have the ReLU here, then we have these normalization operation, and we get the numpy, because we don't need the PyTorch tensor, we need a numpy output. Now we're going to clean the hooks and return the GradCAM. So I hope you understood this main function. So simply what we are doing in this, we are just first we get the layer name, we have you can say we get the gradient value and the activation value, then we perform this, and then we initialize this GradCAM, and after that GradCAM we use these weights to generate it to 2D attention heat map, and after that we pass it via the ReLU and perform a normalization operation, remove the hook and return the GradCAM. So now let's move back to our another function. So before that, yeah, let me also give you a simple function, because we're gonna need it again. So because we are having a heat map, so we need to overlay or superimpose that heat map on the original image, and that is what this function do. So we have overlay heat map on image, it take image as numpy, then heat map also as numpy, then alpha value. In my previous video I've shown you how you can overlay heat map on the image. You can watch that for more detailed content. So here what we do, because we can use any layer to generate the heat map, and that layer may have small size, large size, we don't know. So what we do, we resize the heat map to the size of input image so that they both are equal. Now we know heat map is normalized, so its value would be in the range of 0 and 1. So we multiply it by 255 to convert its value in the range of 0 to 255. Then we apply a color map, that is jet. So this color map specifically used on these heat maps because it helps us to show which region the model is focusing on. So now we use this cv2.add weighted. So we have image, we apply it alpha value, then we have heat map, then we have another beta this 1 minus alpha value, and then we have this value which we would add in the entire equation. For now we don't need, so we say it is 0 and we get our superimposed image. So this is how it works. So next we get a GradCAM here. So we finally are getting a GradCAM. Now what we need to do, we need to get a superimposed image, or you can say the GradCAM image. Okay, so we call it cam image. Now we need to create a binary mask. Okay, so here we have our RGB class mask, and simply we create a binary mask. Then what we do, we concatenate first original image, then GradCAM, then binary mask, and we save it. Okay, so you can see we have this simple line separating the original GradCAM and binary, so that there is a small white distance between them. And here you can see save image, line, cam image, line, and binary mask. And we simply save it using cv2.imWrite operation. And we also check if that specific folder exists or not. If it does not exist, we create it. If it does not, if it exists, then it's fine. So now we are complete with our. So what do we do? First of all, let's see from the encoder. Okay, first encoder, where the first encoder is focusing on. So let's run it, because encoder might, and that to initial layer, we don't know where that initial layer is focusing on. Okay, so let's go in the GradCAM specific. So you can see this is the first encoder block, and here we can simply see that the model is not focusing on any specific thing, but we specifically can see these edges the model is focusing on. Okay, so here you can see it's focusing on the region, on the background region kind of, and this is the read1 class. The mask is none. So here you can again, you can see it focusing on edges of leaves. So we can say the initial layer also have some idea where the what we need to focus on. Now let's do one thing and move to the encoder 4. So we can simply say E4 and save it and again run it. So now we can easily see for each layer. I'm running it for 10. You can run it for entire set of images. E4. Now we can see that model is slightly focusing on some area, but because we are using an encoder, so it would not entirely give you a perfect heat map where it should focus on. This thing we would get in the decoder part. Let's see on this. Yeah, now things are a bit right. We can see it's focusing on the stem, some part on the leaf. So some things are generated, but not entirely that good. Here the masks are also big, kind of blob size, but still the heat map is not that good. So we can go to decoder. Okay, I should minimize this. So we can say D1, first decoder con 5. I hope you know why this name and how exactly do we get this. So it's done. Let's move to the folder. Okay, decoder 1. Now we can see heat maps are getting clustered in specific part. Now they are not scattered like randomly some line something. So the blob kind of structure, either they are there or they are not there. Now let's move to the class 1. Okay, now we can easily get good results, and you can see the even decoder 1 is focusing on the right part of the image where it should. So with this way you can easily see where the decoder is focusing on. Okay, and like with this I get one idea. Maybe we can use these heat maps and pass it them to the SAM, SAM segment anything. We can use this heat map, convert them to a simple binary mask. From there we can get the bounding box and feed those two as the prompt, the input image. Maybe we can get the mask also, and maybe some kind of we can do in future. Yeah, and here if you see we don't have any specific class mask for here, so it's not it's focusing on everywhere and not on everywhere, so not specific. Now let's move to class 2. Again we get good results, and if you observe the image where we don't have any specific mask, it's not focusing on anything specific. Now let's move on to the last decoder, that is G4. And I think this should give us final result because it is the last decoder and it is directly responsible for generating the fine segmentation mask. So its heat map should nearly be equal to ground truth. And here you can see, we can simply see the heat map and we can clearly see that model is specifically highlighting, the heat map is specifically highlighting the leaves part. See, so we can clearly see. Now move to the class 1. See, here we don't have any mask, so none. See, so you can see the model is, the last decode is fucking fine. And maybe if we train this model even more, so we would get finer heat maps. So I hope you learned something from this video. And if you found this interesting and learned something from this, so please make sure to like the video, share it, and if you have any query, comment it down, and do subscribe the channel at the end, because now I'm going to try to continue. I know everywhere I say this, but I don't continue, but I'll try to put few the videos a month so that even I learn something. So that's all for this video. You can check the description for the code and rest of the thing. So thank you. Have a nice day.